Good morning, everybody. I introduce myself. My name is T. Henson. I am working as assistant professor in the Department of Mathematics, St. Joseph's College of Arts and Science, Cuddalore. I am going to teach ordinary differential equation for first MSc Mathematics. Unit 3. The topic is Wronskian and linear independence. Now I am going to give the definition of Wronskian. The Wronskian of pi 1, pi 2, pi 3, pi n of n solutions pi 1, pi 2, pi 3, pi n is defined to be a determinant that is Wronskian of pi 1, pi 2, pi n is equal to first row we have pi 1, pi 2, pi 3, pi n. Second row we have pi 1 dash, pi 2 dash, etc. pi n dash. In the last row we have pi 1 n minus 1 dash, pi 2 n minus 1 dash, etc. pi n minus 1 dash. So this is the definition of Wronskian. Based on this definition, now we are going to see a theorem. If pi 1, pi 2, pi 3, pi n are n solutions of LOA equal to 0 on an interval I, they are linearly independent if and only if the Wronskian of n solutions is not equal to 0 for all x in the interval I. Now we are going to see the proof. First, we assume that the Wronskian of n solutions not equal to 0 and we prove that the solutions are linearly independent. If there are constants C1, C2, C3, Cn such that this linear combination is satisfied, C1 pi 1 of x plus C2 pi 2 of x plus etc. Cn pi n of x equal to 0 for all x in the interval I, then clearly we have these equations pi 1 dash etc. pi n dash of x equal to 0, then C1 pi n minus 1 dash of x plus etc. Cn pi n minus 1 dash of x equal to 0 for all x in the interval I. For a fixed value x in the interval I, and the equations, the above equations 4.1, 4.2 are linearly homogeneous equations satisfied by C1, C2, C3, etc. Cn. The determinants, the determinant of the coefficients is just Wronskian, which is not 0. Hence, there is only one solution to this system, namely C1, C2, C3, Cn equal to 0. Therefore, the functions pi 1, pi 2, pi 3, pi n are linearly independent on the interval I. Conversely, suppose pi 1, pi 2, pi 3, pi n are linearly independent on the interval, we have to prove that Wronskian of x naught is not equal to 0. Suppose if you assume that Wronskian of pi 1, pi 2, pi 3, pi n of x naught equal to 0 for a point x naught in the interval I. Now we see that. So this implies that the system of n linear equations C1 pi 1 of x naught plus C2 into pi 2 of x naught plus Cn pi n of x naught equal to 0. Then C1 pi 1 dash of x naught plus etc. Cn pi n dash of x naught equal to 0. Then last equation C1 into pi 1 n minus 1 dash of x naught plus etc. Cn into pi n n minus 1 dash of x naught equal to 0 has a solution C1, C2, C3, Cn where not all the constants C1, C2, C3, Cn are 0. Let C1, C2, C3, Cn be such a solution and consider the function psi equal to C1 pi 1 plus C2 pi 2 etc. Cn pi n. Now let us L of psi equal to 0 and from the equation of 4.3 we see that psi of x naught equal to 0, psi dash of x naught equal to 0, etc. Psi n minus 1 of x naught equal to 0. So from the theorem 3 it follows that psi of x equal to 0 for all x in the interval I, and thus C1 into pi 1 plus C2 into pi 2 plus Cn into pi n equal to 0 for all x in the interval I. But this contradicts the fact that pi 1, pi 2, pi 3, pi n are linearly independent on the interval I. Thus, the supposition that there was a point x naught in the interval I such that the Wronskian of x naught equal to 0 must be false. Therefore, we have consequently proved that the Wronskian is not equal to 0 for all x in the interval I. Next theorem. Let a pi 1, pi 2, pi 3, pi n be n linearly independent solutions of L of y equal to 0 on an interval I. If pi is any solution of L of y equal to 0 on I, it can be represented in the form pi equal to C1 pi 1 plus C2 pi 2 plus etc. Cn in pi n, where C1, C2, C3, Cn are constants. Thus, any set of n linearly independent solutions of L of y equal to 0 on I is a basis for the solution of L of y equal to 0 on the interval I. Now we see the proof of this theorem. Let x naught be a point in the interval I, and suppose pi of x naught equal to alpha 1, pi dash of x naught equal to alpha 2, etc. Pi n minus 1 dash of x naught equal to alpha n. We show that there exist unique constants C1, C2, C3, Cn such that psi equal to C1 pi 1 plus C2 pi 2, etc. Cn pi n is a solution of L of y equal to 0 satisfying these conditions. Psi of x naught equal to alpha 1, psi dash of x naught equal to alpha 2, etc. Psi n minus 1 dash of x naught equal to alpha n. By the uniqueness result of theorem 3, we then have pi equal to psi, or pi equal to C1 into pi 1 plus C into pi 2, etc. Cn into pi n. So the initial conditions for psi are equivalent to the following equations for C1, C2, C3, Cn. So C1 into pi 1 of x naught plus etc. Cn into pi n of x naught equal to alpha 1. C1 into pi 1 dash of x naught plus etc. Cn into pi n dash of x naught equal to alpha 2. Proceeding this, we have C1 into pi 1 n minus 1 dash of x naught plus etc. Cn into pi n minus 1 of x naught equal to alpha n. So this is a set of linear equations for C1, C2, C3, Cn. The determinant of the coefficients is Wronskian of x naught, which is not 0, since the pi 1, pi 2, pi 3, pi n are independent. Therefore, there is a unique solution C1, C2, C3, Cn of the equations, and this completes the proof. Thank you. Thank you.